In this lesson, you'll be learning how to find the correlation coefficient, which is R, for linear regression in statistics. The correlation coefficient, lowercase r, measures the correlation. You could say correlation, or you could say association, or you could say relationship between two variables, usually x and y. So if you just think about the word correlation, then you're basically figuring out how closely related two variables are. So in linear regression, it's bivariate data, which means two variables, and you're assessing how closely related these two variables are. So for example, height and wingspan. If you wanted to see if those two variables were related, you could run this regression analysis on it. There is a formula for the correlation coefficient, and this is the formula. Looks a little intimidating, but it's really not. It's mostly just subtracting, dividing, multiplying, adding up, and then dividing again. So all really simple operations. It just looks a little scary. So I am going to show you the formula so that you know where this value comes from. And then obviously I'm going to show you the calculator too, because that's how I run things. So I have the steps here. Basically what's happening is this is the formula for a z-score. And so we're finding the z-score for every single x value in the x variable, and then every single y value in the y variable, multiplying those z-scores together, adding them all up, and then finding basically an average of the sample. This in -1 means sample. The correlation coefficient R will always be in between -1 and 1. If it's not, you've done something wrong. A value of -1 indicates a perfect negative linear correlation. A value of +1 indicates a perfect positive linear correlation. The sign of R and the sign of the slope in your linear regression equation should be the same. If they're not the same, then you've done something wrong. The closer the data points cluster around the line, the stronger the association is between the two variables. So the -1 and 1 is kind of the scale, and R is going to be a value in between this scale, and that's measuring how close the variables are associated to each other. So the closer it is to 1 or -1 means the more, the tighter the data points are on the scatter plot. So I have some examples down here. I've got 4 different scatter plots, and I've got the graph of the data points on there. And this is a multiple choice problem. It's set up kind of weird, but you have these answer choices down here, and you're trying to match the correlation coefficients with the appropriate graph. So I'll get you started just to kind of get you an idea, give you an idea. My first answer choice is R equals -1. -1 indicates, first of all, negative means it's going to be falling. And then 1 indicates it's going to closely resemble a line. It's going to mean that your variables are following a line very closely. So you look for the one that's falling. That's only these two. And 1 indicates a very strong linear relationship, which is this one. This is R equals -1. Now I want you to match the other 3 and see if you can get it, and then come back and check. Hopefully you got C, D, A, B. And a quick way that you can decide which is which is if you take a pencil and circle the data, we can see that this is clearly negative. And if our choices are coming down to 0.89 or 1, it more closely resembles 0.89 because there's a little bit of spread in the data points, whereas this one is a very strong linear relationship, negative. And then this one is a very strong positive relationship, which is associated with an R value of 1. So hopefully that kind of gives you an idea as to what R is referring to. And then you can also see that if we did a linear regression equation for this problem, it would have a negative slope, which matches the sign on R. I have a data set down here, which is the same data set that I used in the linear regression video. So these are calculus students, I believe. It just says 8 students, so not calculus. And it is their study time versus their test score. And we're trying to see how strong the relationship is between these two variables. So if we go back to our formula, in our formula, we're going to need x bar, which is the mean of x, y bar, which is the mean of y, s sub x, which is standard deviation of x, s sub y, which is standard, you get my point here, and n, which is the number of data point or observations, sorry, number of observations. So I would recommend, if you're doing something like this by hand, I would recommend becoming very comfortable with your calculator. So you can find the mean of these very easily. Finding the mean is not hard. But if you can eliminate error early in the problem, then it's going to ensure that you have less error in your solution. So if you can make sure and either double check, if you're doing it by hand, just double check that you're getting the right answers, or you can use your calculator, then you're going to have less error. So in the notes it says 1 var stats, but actually there's 2 variables, x and y. So instead of 1 var stats, we're going to use 2 var stats because there's 2 variables. Now I want you to go to your calculator, and you might need to pause it, but for the sake of time, I've already input the data. So you're going to go to Stat, Edit, and you're going to input the X values in L1 and the Y values in L2. If you're not using L1 and L2, that's totally fine. Just make sure that you make note of which columns you did use, because it's going to make a difference when we use our calculator. So I used L1 and L2. To prevent user error, you want to make sure that you have typed in every observation correctly. 1193, 1680, 1385, and so on. And you'll just check all of those to make sure everything's correct, okay? And then you're going to go to second mode to get out of there. That'll bring you to your home screen. If you have not turned on your diagnostics, you might do that now. You go to second 0, which is the catalog, go down to diagnostics, hit on, and then we're going to go to stat calc. And my second option is 2 var stats. That means 2 variable statistics. And then with that, you can see in parentheses the X list, the Y list, and the frequency. I don't have a frequency, so that's not going to matter. So I'm going to click that one. And then my X is in L1. So I'm going to do second 1, comma, my Y is in L2, second 2. Close it, enter. And this is going to bring up the descriptive measures for X and Y, which saves me a lot of time. So X bar is 15 and Y bar is 82.75. The mean of X and the mean of Y. Save me a lot of time. And then also standard deviation. Standard deviation is pretty tedious by hand, not hard, just tedious. And in my calculator, my 2 var stats, you can see it's already done. So nice. So the standard deviation of x, sample standard deviation of x is 4.63, and sample standard deviation of y is 5.65. You'll notice the one below it has sigma. That stands for population. This is not a population. It is a sample of 8 students. So make sure that you're using this sample standard deviation. And then we're going to use those values to help us fill out this table. I always like to use tables when I'm doing complicated formulas like this one. And one of the things that I didn't note in here is that N is 8. There were 8 observations. So what you're going to do down here is you're going to find the z-score for every single observation in each variable, x and y. So I have my x values listed out in a column, my y values listed out in a column, and I'm going to find the z-score of each value. Z-score represents how far that value is from the mean. So we're finding the distance, you know, the z-score is like how many standard deviations it is from the mean. So you're finding the distance it is from the mean, dividing it by standard deviation, and that gives you how far that one specifically is. So go ahead and fill out the table. As a standard or as a rule of thumb, you generally want to go 1 decimal place farther than your raw data. Our raw data are whole numbers. So we could go 1 decimal place. I'm actually going to go 2 decimal places because I'm super paranoid, but 1 decimal place is adequate. So if you could, pause the video, try to fill out this table, and come back and check it with mine. While you're working, I want to show you a little life hack. Since we're typing in the same thing over and over and over again, to save yourself a little bit of time, you can type it in once, and you'll notice that when I typed it in, I have the numerator in parentheses to show the calculator that this is the numerator, and then divide by the denominator. The denominator is just one number, so I don't need a parentheses. And then instead of retyping it over and over and over again, I'm going to do second enter, and that brings back the last line. And then I am only wanting to change this number, so you can scroll over to that number, or if it's touchscreen like mine, you can just tap it and change only that number, then hit enter. And you're going to do this for every value. So second enter, change this value. So once you've found the z-scores for every observation, go ahead and check and make sure that yours are the same, if not really close to mine. If you notice any rounding error, hopefully we figure that out before we finish the problem. But for the most part, these all should be pretty accurate. If you went to 1 decimal place, then yours might be slightly different than mine. If you went to 3 decimal places, again, might be slightly different, but we should all end up with about the same value. And I want to point something out before we go on to finish the table. If you notice the sign on the z-score for x's and the z-score for y's, and you compare the signs. So in the first row, we've got negative, positive, positive, negative, negative, positive. They have opposite signs. So this is going to indicate something about the relationship between the 2 variables, because when we find the product of the z-scores, those signs are going to play into that. So I want you to pause the video, go ahead and find the product of the z-scores, and then lastly, add all of those up. So when you multiply your z-scores, you might notice that you end up with all negative products, because positive times negative shows you have a negative product. And what's happening here is we have an inverse relationship because they're opposite. So as one is rising, one is falling, basically. I'll show you this in a second. It does relate to the linear regression relationship. If you remember from my linear regression video, we found that the linear regression equation had a negative slope, which indicates a negative relationship. And this R value is going to confirm that. So the sum of the z-scores, the sum of the product of the z-scores is negative 4.89. Now we know that an R value is supposed to be in between -1 and 1. So we're not done yet, okay? We have to keep going. So let's continue to the next page. I have a reminder of the formula where we found the z-score for each value. We multiplied those. We added them all up. And now the last step is to divide by n-1. So we got negative 4.89. We're going to be dividing that by n-1. We know that n is 8, and 8 minus 1 is 7. When we divide these, we will get negative 0.699 if I were to go out one more decimal place. If you didn't go to as many decimals as I did, in either case, you should get about negative 0.7 for one decimal place, because that would be appropriate for this problem. I mentioned earlier that I'm paranoid about my rounding. And the reason for that is because if you round too much early in the problem, then your final answer is going to end up being way off. And so generally speaking, when I'm going through this part of the problem, this big table, I'll usually go a little bit further than I actually need to. And then I won't round to one decimal place until the very last step. And that's going to prevent a lot of error. So as you go forward in statistics, when you're doing things by hand, when you're working on the formula, you might go a little bit further than the rule of thumb, and then use the rule of thumb as your last step. So we got negative 0.7 for our R value. We have an R value of negative 0.7. Remember that the sign indicates the type of relationship, and the value indicates the strength of the relationship. So there is a pretty strong negative relationship or correlation between, we're in a room, study time and test score. 0.7 is pretty strong. That's pretty close to 1, or -1 in this case. So the numerical value represents the strength, and the sign represents the direction of your correlation. And so now we know how to do it by hand. Now we know where these values are coming from. Let's do this in the calculator. It's a lot faster. So we're going to go to our calculator. This is part of linear regression. I already have my data in the table. So I'm going to go to Stat, Calc, Linear Regression. Mine is number 9. Yours might be something different. It's L1, L2. Make sure that your diagnostics are on. If your diagnostics are not on, your R value will not show up. So if you're doing this and your R value is not showing up, then your diagnostics are off. And remember to do that. You go to second 0, scroll down to D in the catalog, turn diagnostics on. Enter. And we can see down at the bottom, we have, well, at the top, we have our linear regression equation, our A value and our B value. And then down on the very bottom line, look at that, R value. So from the calculator, we got R equals negative 0.7. So that was a little bit faster. But if you are doing it by hand, that's a great way to check your answer. If you don't have to do it by hand, then I would strongly recommend using a calculator like this. It can also, calculator like this. We'll just stop there. So that is all I have for the correlation coefficient. I hope you enjoyed it. If you have any questions, please let me know and I'd be happy to help. See you in the next one.